Now another important point you to understand here, how this number of bits in the field, certain field, has been decided. Okay, so for example, there are certain number. Let's start with in art type. Okay, so let's start with this art type. This art type, let's say, let's take this register fields, right? Why there are 5 bits? So if you recall, your register file in the MIPS has 32 registers, right? And they are indexed as 0, 1, 2, 3 up to 31. Now think of your how many minimum number of bits you need to represent 32 items. Okay, 32 index 0 to 31. So that's a number system problem, right? And we know it is log base 2 of 32, which becomes 5. So exactly that's why these register index fields are 5 bits, because your processor's register file has 32 registers in it. Now, how about the shift amount? Shift amount, if you think, we are talking about the 32-bit processor here, right? So if you shift in any direction, left or right direction, if you shift the bit more than 31 position, your result become 0, right? More than 31 position. So shifting a bit pattern more than 31 will cause a 0 result, right? So you effectively you need to shift between 0 and 31 to make some sense about that result, right? You don't need to like shift a bit pattern which is goes out of the scope, becomes all 0. So that's why your shift amount is also bounded from 0 to 31, because your target processor MIPS we are talking about here is 32 bit, right? So log base 2, 32 is 5, right? Imagine if you are dealing with a 64-bit processor, then shift amount field would be log base 2 of 64, which is 6-bit, right? But for us, it is 32-bit processor, and that's why it becomes shift amount will become your 5-bit, all right? Now, opcode and function, right? This is more like an assembly language design problem. It depends on, for example, it depends on how many total number of opcodes we want to provide, and also if there are other spaces. Sometimes we keep some extra fields there to based on. So there are many factors depending on what these two fields are given. Function are given 6-bit each. Okay. First of all, we don't need more than 20 bit field to represent 3 register and 1 shift amount. Then we are left with 12 bit. Now, depending on what we want to do with that 12 bit, whether can I put 4 bit here and like 10 bit there. Yes, but remember, this 6 bit is also, this position is also used to determine code for the other instruction other than art type, right? So you need to also take account of that list of instruction, how many you are going to provide there. So it has been determined that 6 is the optimal number there. So that means we can have 2 to the power 6 different number of opcode, which can be associated with certain instructions. All right. So we have like 60. That means we have can be total 64 opcode. So 64 instructions. Okay. Now wait a minute. Your art type instruction opcode field is all 0, and they are differentiated with another 6-bit function code. So how many different function code we can generate with the 6-bit? 2 to the power 6, which is 64. So 64 function code means 64 different art type instruction, which all possess or all have this opcode of all 0. So non-art type instruction in the MIPS, in that case, in our 32-bit processor, R type instruction would be 63, number 63, right? So there can be 63 non R type instruction and 64 R type instruction. So total, with this format, total number of instruction a MIPS processor can encode is 127, right? 64 plus 63 is 127. In fact, if you look at the list in your textbook first page, it is way less than 127 instruction. And believe me, with that limited number of instructions, all the programs of the whole world can be written. Okay, be it a like movie application, be it a word processing application, be it a scientific calculation application, be it a Facebook platform, be it the Android platform, doesn't matter. With that limited number of instruction at the assembly language, one can implement anything in the whole world. Okay, anything. So that is the basic beauty of having basic level instruction. So all you need to do, whatever complex way you want to define your high level language, need to have a compiler which can generate and translate your high level program into corresponding equivalent assembly level program with that limited number of sets in hand, instruction in hand, and then you just translate into machine code and your computing system will perform or execute your complex program. All right, so that's about the number of bits in the fields and so on and so forth. Then we also need to you understand what is the range you can provide in the immediate field, because 16-bit unsigned has certain range, and 16-bit signed 2's complement 16-bit signed has another set of range of the values. So you need to understand that part as well. And also you need to understand this other jump or address field, which will dictate you how far you can jump. Basically, it has also limit. It is 26-bit, so you know what is the range of that address field is. So you have a limit there for jumping, and we'll be discussing more about this jump in detail in later. Okay.